class. As some of you have been asking questions, so please, you are welcome to ask more questions during my office hours, and Felipe will also have office hours on Wednesday to answer any questions about homework 4. Okay. Next Monday, exam 2. So we'll have the second exam next Monday. And that just to clarify, if it wasn't already clear, the second exam is going to be just fluid mechanics. So it is just part 2. We don't have cumulative exams in this. So it will just literally be from exam 1 and then between whatever we have covered, which is fluid mechanics. Based on the feedback, on mid-sem feedback, we'll have 2 changes. We'll have 10 minutes extra. So it will not be 80 minutes. It'll be 90 minutes and the length will be same. So will not increase the length. So it will give you just extra time in case you felt you were a little rushed or you just didn't have time to think through some of the questions. And then in advance once the homework is submitted, we'll also, in addition to a practice exam, we'll post practice conceptual questions. So these will be just, just for a practice. If you felt like some of the conceptual questions were a bit harder to, kind of get an exam, so we'll post that as again based on the midterm feedback. For this second part, because there's a lot we have covered, I'll do a mini review today, but then I'll do another review again on Wednesday, the second part of the class, as I did for the first exam. So any questions for the homework and or the exam? Anything that's, and again, open book, open notes, you can bring your laptops, whatever you want. And it will be similar in terms of like, the rules. Any questions for exam or homework? Anything that's not clear? All good. Okay. And from today and even Felipe's last lecture, we have been recording using a microphone. So I believe hopefully the voice is better. Some of you mentioned that while listening to the lectures, the voice wasn't as clear. And so hopefully this will help at least a little bit. Okay. All right. All right. So let's get started. So today what I want to do, the class will be basically 2 parts. The first part is I just want to review and kind of put in context whatever we have discussed in fluid mechanics, that is unidirectional flows, unidirectional flows, lubrication approximation, and then finally the creeping flows. I kind of review. This part will have some sort of like many clicker questions, so that I want to kind of get through some concepts just to kind of again show you. And then in part 2 of the class, that is after the break, we'll start talking about inviscid flows, which is essentially a different kind of flow where Reynolds number is actually infinity. So we have been thinking about small Reynolds number. We have been ignoring inertia till now. The second part of the class will switch gears and start to basically completely ignore the viscous term. We'll now start to focus on inertia. Okay. So we'll get that to in part 2. So in part 1, this is not something I'll spend a lot of time on, but obviously we have derived the Navier-Stokes equation. We also discussed the boundary conditions. And boundary conditions, we discussed 3 types, which we'll basically use in this class. One is fluid solid, fluid, but velocity equal to 0, which is hydrostatics, or a liquid air. Okay, so these are the 3 categories of boundary conditions that we have been using. We do not use the liquid because that's the much more complex set of equations, and that's beyond the scope of this course. But these are our governing equations, and these are our boundary conditions. Okay, whatever we discuss in this class, these equations and boundary conditions are always valid. Okay, so just don't forget that these equations are always valid. You can always use them. But the problem is that if you want to use them right away, we'll always end up in, these are too complex of equations to solve. And that's the problem with Navier-Stokes equation, which remains unsolved today, is that you can never really solve this full equation completely for all scenarios. Okay, so that's why a general solution does not exist. So that's why we have been trying to find different approximations to make our life easier. Okay, so that's the kind of the idea. Just don't forget that these equations remain always valid. All right. The first approximation, which you covered it in your last homework, was hydrostatics, which is essentially when velocity is 0, shear stress goes away, and you can just solve for pressure. And we covered 2 kinds of problems. One was buoyancy force, and the second was contact angles, right? Where basically we had, and the stress vector, remember, because there is no shear stress, it was simply minus Pm. Okay, and then you just integrated over that to calculate the pressure force. And you calculate force. Okay, so that is something we discussed in in the simplest approximation. Then unidirectional flows, we started talking about them, and I just want to emphasize one thing. So in unidirectional flows, we started thinking about flow like this, where fluid phase is here, and we have the pressure-driven flow. we calculated, velocity profile such that Vx was a function of y and Vy was exactly equal to 0. Okay. So that is the one example of unidirectional flows that we did cover earlier. In your homework 4, there is another example that I want to just mention briefly. Is, for instance, let's imagine this is a sphere, okay, and you are kind of rotating it with some it's a rotational flow. So rotational flow in spherical coordinates, we can have Vr, V theta, V phi. Okay. So if I'm rotating it around the z-axis, which velocity component do you think can be non-zero? All of them, yes. V theta. So remember, V theta is this angle. So if I'm rotating like this, then it's not rotating in this direction. It's not creating any disturbance. It's creating disturbance in the xy plane, right? If it's the z component, then the disturbance will be in the xy plane. XY plane are denoted by V phi. Okay, so this is a long derivation for this problem, but basically you can show that only V phi will be not equal to 0. So this is a kind of unidirectional flow which we have not discussed in the class. And I briefly mentioned this because there is a supplementary video on this. If you would like to take a look, you don't have to watch the full video, but just to kind of get an idea of how do you approach a problem where you can argue there's only one velocity component which is non-zero. It's a unidirectional flow because of rotation. And in your homework, there is a problem like this where you're rotating the plates. Okay, so you're rotating the plates like this, cylindrical plates. And basically, I believe it's only V theta not equal to 0, and you will see this in your homework. This is homework 4, problem 3. Okay, I just wanted to mention that, just to kind of give you context, is that when only one component of velocity is not 0, that is the case of unidirectional. Okay, is there a questions? Anything? Question about this? Yes. Yeah, so it's a good question. So I mean, there's a little bit of like sort of an intuition there as well. So you can imagine if you're rotating like this, right? I shouldn't expect anything in the z direction, like going up and down in the plate. So let's imagine there are two cylinders like this, right? Z direction is this between the plates, and r and theta are within the plane of the plate, like a cylindrical plate, right? R velocity of r direction means something that is going in this sort of, let's say this, imagine this floor is a plate. Then if I'm radially going outwards, that's my VR. When I'm rotating, it's kind of like, as you can see, imagine it's not something that you can expect. What will happen if something is circulating like this, which is your V theta? What can change though is that V theta can be a function of R. So don't forget that I'm not saying that it does not depend on the radial direction, just that the radial component of the velocity is 0. So that's what if you solve the homework problem, it tries to walk you through the steps of how it is dependent on R, and then kind of you can find the solution. Okay, so it is just kind of rotating like this. So that's similar idea here, that when you're rotating, it's kind of a little unintuitive to expect to have a disturbance in any other direction. Okay, and by the way, these might look like a simple scenario. Why are we interested in this? These are very commonly used in rheology. So if any of you are going to be doing any material characterization, a relative motion of cylinders or like a cone is a very common geometric problem in rheology. So that's how it comes. Literally, you solve these equations and you get results with viscosity and shear rate and so on. Any other questions? Please feel free to ask questions here. All good. Okay. So basically, unidirectional flow, think of a pressure-driven flow or a shear-driven flow in a flat plate. But don't forget that rotational flows can also be can also cause unidirectional flow. Then next thing we discussed was nearly unidirectional flow. Nearly unidirectional flow. In that case, we had an x and a y, and we showed that Reynolds number times h by L should be smaller than 1, and h by L should be smaller than 1, where this is 2h. and this is L. Okay. So this is basically was the idea, a small length and a small Reynolds number times h by L. And we said Vx is a function of both x and y. Vy is a function of both x and y, but Vy by Vx is much, much smaller than 1. And we also meant pressure is smaller than x. Okay. So this is the second kind of problem we did in nearly unidirectional flow. And we also did another problem with a ball bearing problem where something was sliding here with velocity u. And in that case, there was a force balance. I highly recommend this kind of at least going to the notes in the supplementary video here of how different forces come out using order of magnitude analysis. I will do some clicker questions in a similar problem in just a few minutes. But if you're not sure, please do make sure to watch, like kind of at least go to the notes for how to think of force balance when your geometry is changing. Because I think it's very instructive and very helpful to understand what happens in this problem and how forces act. Because that's the most common mistake I've seen among students is kind of misunderstanding force. Because now you have shear stress, you have pressure combined, and you have geometry changing. So it's sort of like a little more complex. For instance, I just want to mention one thing, as you'll find in that video or notes, is that force along the x direction is constituted by both pressure and the shear stress, whereas in the y direction it's just pressure. If I give this problem to students, most of the time I've seen students think shear stress is only x and pressure is only y. This is a common thing, but actually pressure also impacts the x direction. If you solve the problem, you will see that that does happen. Okay. So I just want to kind of emphasize that pressure can contribute in your x direction as well. So this is the problem. In this problem, remember that in both of them, our invariant was flow rate. Invariant was flow rate. Okay, Q. However, and in your homework 4, problem 1, you will do a similar problem with, and some of you have already done it, is using like a sinusoidal cylindrical pipe, where also invariant is like a flow rate, capital Q. The small q is flow rate per unit width because third dimension we were ignoring. Here there's a cylindrical pipe, so it's easier to do the full flow rate. But then in your second homework problem, homework 4, problem 2, you have something like this here. Which is an air hockey problem, and some sort of velocity is coming from the from the board and is keeping this air hockey puck afloat, Z and R. And this is, I believe, radius R, and apologies if I messed the symbol, but I think it is capital H or maybe small h. But we have been given that h by r is smaller than 1. Okay. So now I have a question for you. In all of these other problems, geometry is fixed, right? Then why should I? And naturally, you can imagine that the flow will, go something like this. Why should I think of this as a nearly unidirectional flow problem when the geometry is fixed? Shouldn't I just expect this to be a unidirectional flow problem? Or why is this nearly unidirectional flow and not unidirectional? Okay, so yeah, so good answer. So answer is radial component dominates, but there is a slight implicit statement that means is that there is a z component because of the perforation, which is causing this air, which you're putting the air in the z direction, but the r component dominates. So there are two velocity components which are non-zero clearly, and one of them dominates. So if I didn't, let's say I did not have anything like zero, I did not put anything velocity like this, then there is no reason for it to have any z component. So because both components of the velocities are non-zero, but one of them dominates, that is a unidirectional flow. In general, in other problems also, look at the other cases. Why is there a radial component of velocity? That's because there is a geometry change. Here, the radial sorry, the smaller component of the velocity. Here, the smaller component of the velocity because of the porosity. Okay, so the reason for a smaller component of the velocity could be the geometry change or something like porous, but one of the component of the velocity dominates. Okay, so that's clear. Now, in this problem, what you will do is you will do the same problem. What you will start with, lubrication equation and everything. But one of the interesting questions somebody asked me, and I think it's a very insightful question, is that this air, the disc is a float, and so at the end of the day, you will calculate the force and balance it with the weight of the disc to say, okay, it's stationary, so that's the force, and that will give you kind of a relationship of the force with the mass of the disc. But if there is gravity, how can I use any of the analysis? I have ignored gravity. I mean, in this kind of, when I write formula, let me just write it here. If I say this here, dP by dr is equal to mu del square vz, vr by vz square. Okay, so this is kind of how I will start my lubrication, right? I'll take the pressure gradient and argue it is only a function of radius. Then mu del square vr by del z square. So it's del z square in the bottom as well. And this is how I'll start. And I'm saying there is gravity because that's what is holding the weight of the disc. But there is no gravity here. Sorry,
is the dynamic pressure.
So the question is the dynamic. So the answer is there's a dynamic pressure. So that's a good comment. We haven't discussed dynamic pressure, so I will let also the please go ahead.
Well, we're solving these equations in the fluid, and in this case, the pressure just dominates gravity. Right.
Good. Okay. So almost there. So that's exactly the idea. Is that note that we argue pressure is in the radial direction, right? Implicit in that is that we have done a z direction balance, right? A z direction balance. If the gravity is only in the z direction, so that means the pressure that changes in the z direction, the effect of gravity is only going to be in the pressure in the z direction. And because we have already argued that the z dependence is small, we can ignore gravity in the radial direction because there is no gravity in the radial direction. Now imagine if I flip the system, somehow there was gravity in the primary direction, then I will have to include gravity. It's not that gravity doesn't exist, it's just that in this problem, it is not affecting our pressure. Okay. If I flip the system somehow, like there is like a air hockey table which has like a disc like in the flow in this direction with gravity, the gravity is going to impact it. So just want to clarify that so that you can understand. So you will do this problem. I want to emphasize one thing in this problem is that there is a okay, I'll talk about the squeeze flow problem next. But was there a question here? I thought somebody raised a hand. All right. Okay. So you will do a force balance in your homework, and then balance it with the weight of the system. So just to kind of emphasize one thing here is that this is a disk. So remember there is some F hydro. And there is some some gravity, F gravity. So F hydrodynamic, this F gravity has to be equal to 0. Why should this be 0 exactly? Can anybody suggest why should the forces be balanced?
No acceleration.
Absolutely, it's fixed, right? There is no acceleration, so force balances, so mass and acceleration is 0. All right, perfect, great. All right, so now let's go to the next kind of flow. So unidirectional flows, we learned invariants. What are invariants? And by the way, invariant in this problem, as you will do in your homework, is naturally going to be V naught. Okay. We are entering, we are basically pushing some air inside the system. So the invariant is not going to be flow rate, but V naught. Okay. All right. So now let's go to creeping flows. So first we discussed unidirectional, unidirectional. Now let's go to creeping flows. All right. So creeping flows, the idea was simple. The idea was Reynolds number is much smaller than 1, and hence my equations simply become plus rho g is equal to 0. And for practical purposes, we consider gravity free flows. We didn't think of gravity to matter. I mean, it can impact it, but we were just ignoring it, assuming systems with gravity equal to 0. But this is our equation. And naturally, we also have this equation. We just ignore the inertia completely because the Reynolds number is small. And hidden assumption, which will be true for this course, but just so that you are aware, is that the process time scale is comparable to the viscous time scale. Basically, the Strouhal number, which is on the order of 1. That's a detail. I wouldn't worry about it, but just for completeness, I want to emphasize that there is a small assumption there. We'll not worry about that for the purpose of this course. All right. Now, just to sort of briefly kind of recap what we discussed. So just to remind you, these creeping flows are very important and also of my personal research interest. So these are kind of some of the creeping flows in biological systems. So what you see here are these E. coli and different organisms, microorganisms, and all of this happens at small Reynolds number. And the challenging or the interesting feature here is that it's very counterintuitive. It's so counterintuitive, the motion of these microorganisms, that there is a full field which kind of goes behind. It's all small Reynolds numbers. And as you can see, all these papers are here actually 2016 or so. And these are actually pretty new. So this area is very, very, active and kind of very relevant. And then Felipe briefly discussed this idea of that in creeping flows, you have this kinematic reversibility, and that the distance stays constant when you have something falling off the surface. However, if we start to add flexibility to the sheet, this can actually change. So this was for a rigid wall, but then if you have a flexible sheet, there can be fluid soft wall interaction. So some of you may be working in some sort of flexible sheets or some sort of soft materials, and if you have like a small Reynolds number flow with a flexible sheet, there's a very nice paper which kind of shows you, again for 2018, shows you how you can have a drift happening, which is very which first it was very difficult to understand why it doesn't drift, and now it's more difficult to understand why it drifts when you start to have this flexibility sheet. Okay, so these are some very interesting studies that happen here. So the main point here I want to emphasize going from here is that these are time dependent. These are time dependent system, as you see. This image that you see is time dependent, right? And my equation does not have any time dependence. So what does that mean? Why should I, like, isn't that weird? Like that I don't have time dependence in I'm talking about all these phenomena which are time dependent, but then there is no time dependence in my equation. So how? Yes.
Is it because they're position dependent and the time kind of plays into position, which is why it's reversible in time?
So it's a good idea. I think you're almost there. So Colin's comment is basically that the position is sort of like has sort of an impact on time. So more sort of, I would say, a more formal way to describe is that the boundary conditions can be a function of time. Okay, so don't forget that boundary conditions could be a function of time. So boundary conditions can be a function of time. Function of time. Okay. So here I want to go back to the problem that was discussed last week, which is a squeeze flow problem. Is that we are squeezing out flow between two plates. So there is some sort of a VT here. And so you're applying some force here. And then you're trying to kind of push these plates. Actually, we just say V here, let's say. And then this height here. So let me just call it for h of t, just for purposes of this. Felipe did it with small h. And as Felipe had discussed, that basically flow will happen kind of like this. You're squeezing out the flow. And the point being that this R by h here, this is R, this is h. We were given that h by R is smaller than 1. Okay. So in a way, if you think about this, this is sort of similar to the air hockey problem, right? That there is some normal component of the velocity. This is from both directions, but There is some normal component of the velocity. Height is very small compared to the radius. So what is the difference? The difference is that now there is a time dependence. Okay. So there is a time dependence. Now it's not no longer a steady system. It's a time dependent system. So basically it is kind of like a lubrication problem, but with a time dependent boundary condition. And that's why we put it under creeping flows, is that this is a creeping flow where the boundary conditions can enter through a time. We don't say that the system has to be necessarily steady, but when we formally describe lubrication, we assume that the system is steady. So here the system is not steady, it's kind of like pseudo steady. Okay, so you do all of this problem and then you try to find the system. So let's do some quick clicker questions to sort of understand, because this will help you with your homework as well. I want you to think about what is the pressure, what is the scale of the pressure here. Okay, and actually just let me correct one thing. Let's call this capital U. Let's call this capital U. Okay. Let's call this capital U from both sides. So what do you think is the pressure, scale of the pressure? Okay, I just want you to think about the scale of the pressure, how will you estimate it, and what will happen to the pressure. So I'll give another maybe 45 seconds. So take your time if you need a few more seconds to think through this. A hint for those of you are thinking where to start is to write the boundary condition and write the governing equation, and once on the governing equation, apply an order of magnitude analysis. All right, maybe last few seconds in any case, somebody wants to put in their answer. It's great. All right, I'll close the poll now. Let's look at the results. All right, so there's a split. I do want you to talk to each other to see what answers you put in with your neighbor, and then till then I'll write the solution. Okay, so make sure to talk to your neighbors about what answers they gave, and we'll start to discuss this. All right. So the correct answer is B. And let's look at how it is B. So Felipe did discuss this. I just want to emphasize again is that from the continuity equation, we know VR by R is U by H. Note that you have been given the normal component of the velocity. So VR is UR by H. And then here, when you will do scaling here, it's mu VR by H square. And that's where most students sort of make a mistake, is that just substitute VR as U instead of UR by H. So you get a mu UR R square by H cube. Okay, so mu R square by H cube. And now, once you have the pressure, what do you think would be the force? Okay, so you've done the pressure scaling. What do you think will be the force? So I'll give you, let's say about a minute or so. So let's poll this as well. What do you think will be the force for squeeze flow? Correct, yeah. So because it's generally, so that's generally more gravity. And that's a good question. So discuss where there is a effect of gravity.
But you grab it, still those equations.
So discuss. We did that people as a service someone was thinking of extracting dynamic pressure. So it's just a small, don't worry about it. It's even if you write either or, it's the same answer. All right, maybe another 5 seconds so that everybody can get their answers in. Some of you haven't done it, so please do just get a guess if you are not sure, and we'll of course discuss this. All right, so I'll stop it now, and then let's see. Oh, sorry, I forgot to check the results. My mistake. Apologies for that. Forgot to check the results for the last one. Oh, it is. No, it's all right. It's all right. But the correct answer is hopefully, you did participate, so it's all right. But the correct answer is B. And you can think about it like this: is that force is going to be pressure times area, and you will get it out to be just the R square dependence. Okay, so the correct answer is B. Now the confusing part is I have been telling you for a few lectures. Oh, don't ignore the shear stress. Don't ignore the shear stress. And then I'm now saying that it is just pressure times the area. Is that you have to I recommend this, and you will get used to these sort of scalings. Is please do look at the notes or watch the video which formally derives all of this. It literally goes through all the steps and shows you how the full force is calculated on a squeeze through problem. Note that the most generally for by and large, I will say in the normal direction, it's all right to use pressure as the leading in the lubrication flow. In lubrication flow, not in any other case. In lubrication flow, in the normal case, pressure would generally end up dictating, but there could be a parallel component, right? So why do you think there is no parallel component? Do you think like there is shearing happening, right? So shouldn't the disc start to move in the parallel direction because of the force being applied by the fluid? It's a symmetric system, so it balances out in this theta direction, and that's what actually balances out in this parallel direction, and that's what the full video will show you, that there is no tangential force. There is a tangential stress vector, but when you integrate out the stress vector, the force comes out to be zero, and that's important because when you think about your air hockey flow problem, there will be a tangential force as well, but balances out in all the directions, and it's only normal at the end, which remains there. Okay, so don't forget that stress vector times area still has to hold, and at the end of the day, you will see that it just ends up becoming pressure only in this problem. And so in lubrication flow problem, in symmetric cases, that will happen. When will it not happen? It's like something like this here, because you're sliding in this direction. There is actually something that stays over unless there is some symmetry. It generally ends up having both kinds of components in the system. So just want to clarify. Yes, please.
So when you're doing the order of magnitude of
Sure.
force,
Yes.
in the end, it's an integral.
Correct.
only of the stress vector.
Correct.
So you just ignore that. It's just the.
Is that, yeah, so I've definitely skipped that. Yeah, good question. So that would be, I would say, the more correct way to do it is to actually go and say the normal vector. So it is actually Sn. It'll have two components in the normal direction. One would be tau Zz, and then would be pressure. This is what you will get actually. And this is much smaller than pressure is basically what you can have to do if you want to formally show the full system. But yeah, but I would say in case of like in lubrication flow, in the normal component, pressure generally always dominates, so you don't have to worry about it.
So yeah, when you do the
Yes, okay. Any other questions? Anything that's confusing? All right, okay, so now we have discussed, until now we have discussed all the problems where we had either Vy was 0 or another components were like all other components but one was 0, then one was dominant, and then when we added a complexity of a dominant flow with a time dependent system. Okay, so that's until now. And then finally I wanted to discuss creeping flow with two dimensions of velocity. So creeping flow with two components of velocity. Components of velocity. And that's essentially the flow past a sphere. So flow past a sphere like this. Okay. And we ignore the gravity. So ignore gravity in this problem. And then we'll say minus grad P plus mu del square V is equal to 0. Okay. And then del dot V is equal to 0. Now V can have three components, VR, V theta, V phi. This is the sphere of radius R. Okay. U infinity easy. So this was the problem last time which was discussed was flow past a sphere, and the sphere is a rigid solid. In your homework 4, problem 4, you do a bubble, flow around a bubble, and I'll discuss that in a second. But now you had this, so we ignore V phi. We say there is no flow. So imagine like this: if the flow is happening going up, let's say imagine coming from the floor and going towards the ceiling, and the sphere is like this. We are saying it will not happen parallel to this plane. There will be no velocity parallel to this plane. It will just go around the sphere and look like this. Okay, which is a reasonable assumption that there will be no spillage around this at this plane. Okay, it will just go in this direction or around the sphere. And since VR and V theta, V phi is ignored, which is axisymmetric assumption. Now at this point, I want to really emphasize. Can I just directly solve? I mean, technically, I just want to solve for pressure. I also want to solve for pressure with VR V theta. Right? I have the equations written on top. I should be able to solve them. Right? That's the point. That we have three variables and three equations, so we should be able to solve them. And the whole complication or this problem is more challenging is because remember now there is only one length scale. It's not like a channel. We are not thinking about flow in thin spaces, flow in and under confinement. Now we are thinking of flow outside some particle. So there is only one length scale, and that length scale is the radius of the sphere, right? There is no other length scale. There is no other dimension. So if I do an order of magnitude analysis, I will never be able to say, oh, VR is much greater than theta or V theta is much greater than VR. And that's why you have to solve everything at the same order. And that's why it's challenging because there is no other length scale. VR is actually equal to V, roughly equal to theta. And in your home, and you can show it's actually equal to U because there is no U infinity, similar scale as U infinity, because there is no other dimension. Like there is no other dimension, there is no other velocity. So you cannot really simplify the system. From that argument, you can also think about that pressure would actually be similar to mu U infinity by R. Right? That will be the scale of the pressure because there is no other stress other than mu U infinity by R. That's the velocity, that's the length scale. So that's the challenge. And that's why we say, well, this is too complicated. I don't want to solve this equation, three set of equations. I want to simplify my life. And for that's why you kind of, what Felipe derived was that instead of this, your governing equation now becomes either del force psi equal to 0 or E force psi is equal to 0. And that is given in your table. Okay, so I'll let you write it for a second. So either del force psi or E force psi is equal to 0. Okay. So whenever you have a creeping flow with two component of velocity similar to each other, this is your governing equation, and this is basically what is there in this table. Okay, so which is del force. So you check which system you are at, then you just define your velocities here. It's given to you. You don't have to know what your velocities are. So first we are in spherical coordinates. Okay, spherical coordinates. So we check the geometry we have there at this level. VR and V theta. So that's the coordinate that we can solve. So I'll define a velocity like this and VR and V theta like this. Okay. So that's the idea. All right. So my governing equation is this, which I know now. But what are my boundary conditions? Are they in psi? Because the variable I'm trying to solve is in psi. Right? So how are my boundary conditions? How will I find my boundary conditions in the system? Any thoughts? So it's a fluid solid interface, so no slip, no penetration, and then you know the velocity far away. So the boundary conditions though are in VR and V theta. Does everybody agree with this? Any questions about this? Any questions? So how do I go from VR and V theta to psi? Absolutely. So I really want to make sure that you all follow this process, is that we know the VR and V theta. If I write my boundary conditions in VR and V theta, then I can convert them into psi. Okay, convert them into psi. Okay, so you have basically governing equations and then boundary conditions, and you can convert them into psi. Now, should I be able to just solve the system? I mean, you have governing equations and you have boundary conditions. Should I be able to just directly solve? What do you think is the complication here? Sorry? Yeah, I agree. So, but I'm saying that there is a fourth order boundary condition, governing equation, and you will have 4 boundary conditions. The complication is this is a PDE. It has dependence on both R and theta, right? We know that psi is dependent on both R and theta. I cannot do any order of magnitude analysis to say that, oh, well, it is R is much more dominant, theta is less dominant, and so on. It is dependent on both R and theta. So that's why you convert psi of R comma theta, and I will skip over some of the details. Felipe had already provided this in his lectures, is that you can actually argue that it'll become like an f of r times sine square theta, and this comes because of the boundary conditions. Don't worry about this sort of like detail. This will always be given to you in sort of like a homework problem or an exam problem, that you can substitute something like this. But I want to go through the process. So governing equations are this, boundary conditions are in VR and V theta. We convert the psi into FR times sine square theta. Then now you convert both your governing equation and boundary condition into f of r. Okay, into f of r. So first we started with psi, but because our boundary conditions were in VR and V theta, we had to convert them into psi. Then we make the substitution, and then we go into f of r. Now this becomes an ODE that you can solve. So once you get f of r, from f of r you get psi, and then from psi of r comma theta you get VR and of r comma theta and V theta of r comma theta. Okay. So that's how the process works. That's why it's a long problem. It takes time. And then from once you have that, then you can get stress vectors out. Oh, by the way, there's also one last step which we don't do in the class, which is to get pressure of r comma theta. So something you will not do. We'll just give you the pressure, which is even longer problem. So let's not go over there. But I want to show you the process. Okay. Remember this creeping flow, 2 dimensions, stream function. Okay, that's the idea. Then boundary conditions, usual, but convert them into psi. Then convert a PDE into ODE. Then solve for f of r, go to psi of r theta, VR B theta, pressure of r theta, and then stress vector. And then from stress vector, you can calculate force. And that actually is the process to get the force as 6 pi mu u mu r u infinity. That is the Stokes drag. In your homework problem, you will do the exact same process. You will have VR V theta, del for psi. The only difference being that your boundary condition will no longer be no slip. It will be 0 shear stress, because it's a fluid air interface or liquid air interface. And the same process, you do the psi, you get f of r, you get VR V theta, and then finally calculate f. So you do the same process, but for a different system and a boundary condition. So one boundary condition changes the entire flow calculation. Okay. Now this result, this seemingly simple result, I would say has probably had the most impact on fluid mechanics, even other fields. If you have ever used a DLS, dynamic light scattering experiment. You know that you can calculate diffusivity through that experiment, then you use the Stokes drag to calculate the size. It's called the Stokes-Einstein relationship, which basically is in every dynamic light scattering experiment. This relationship is basically is used to understand drags of small particle. It was very important in suspension dynamics. It continues to be some sort of a prefactor for that. Continues to be very important for small Reynolds number understanding of microorganism movement and so on. So it's a really very important result. Since then, there have been corrections to it of Reynolds number, some of corrections, moderate Reynolds number and so on. But I would say this is really one of the most fundamental results in fluids. And somebody basically just derived this in 1850s, if I'm not wrong about the decade, but somewhere in mid 1800s, they derived this sitting at, doing all this calculation. Okay. So this is a very, very classical problem that I just want to review again. So you do this. One small thing we will discuss before we take a break is terminal velocity. So terminal velocity is something you think when a small solid is falling through rho s here like this, and the velocity is vt, let's say. Gravity is g vector. Okay, and what happens is if it's falling through a viscous liquid of mu and rho, something of mu and rho, then basically what you can argue is you can say if it's constant velocity, if something has a constant velocity, the acceleration is 0, right? So the net force has to be 0. So the net force is F hydrodynamic plus F gravity, but F which is the buoyancy force is equal to 0, and we basically say 6 pi mu Vt r, but I will make a minus sign and I will discuss why this is 4 pi by 3 rho s g r cube minus 4 pi by 3 rho g r cube equal to 0, and you will be able to derive that Vt is 2 by 9 rho s minus rho. I believe this should be correct. Hopefully I didn't get anything wrong. And this is your terminal velocity calculation. Okay, and I'll answer Noah's question. Noah had asked me a question, so I'll answer this question now. But this is essentially the calculation is that hydrodynamic force. First, there's a negative sign. Can anybody tell me why there's a negative sign instead of a positive at the top? Yes.
Because it's a force on the ball from the fluid other than on the fluid from the object.
So that is the force on the solid, right? That is also the force on the solid. Stokes drag. Right, because the force is when the fluid is moving. In this case, the fluid is at rest. It's the solid which is moving. So you just reverse the sign, because if you sit on the solid, then the velocity is minus Vt. Okay, does it make sense, Colin? It's the relative motion. So it's a relative motion because in this case, the solid is moving, right? And the fluid is at rest. So if I want to make the solid at rest, it's the fluid going, the opposite direction. So that's why there's a negative sign. Any questions? This is very important. Any questions here? Minus sign? All right, then the weight is simply volume times gravity, and the buoyancy force is the weight of the fluid displaced, and then you can solve to get this velocity. So first thing is terminal velocity is in the direction of gravity if your rho s minus rho is greater than but if there is a liquid, let's say if there is oil, and imagine oil as a solid for now, just ignoring some of the details, then it will go up, then you'll have an opposite direction of the gravity if something is lighter than the water phase or the liquid phase. Okay, so this is the terminal velocity. One quick question before we take a break is since buoyancy force is in the hydrostatic pressure force, which is what we discussed, aren't we double counting the drag force? This was Noah's question, is that we relate to that. Since buoyancy force is the hydrodynamic, is a hydrostatic pressure force, right? We know that. So, and I have already done the full force calculation, stress vector, where we include pressure. So aren't we double counting the buoyancy force? maybe another few seconds. All right. So let's end the question now and let's look at the answers. So most of you say no, which is correct. So, but I want to give a reason. So why do you think you're not double counting? Okay, so sorry is a good sort of argument is that well drag force which you are calculating is sort of like related to movement and it's not really buoyancy. But then my argument is well pressure force is the buoyancy force and I'm including pressure. Then what's the issue here? Any thoughts? So that's where we cheated a little bit. So when I said here before that I will give you pressure here, right? We said this at this step pressure. This pressure was calculated by assuming. This pressure was calculated by assuming minus grad P plus mu del square V is equal to 0. Okay. If this pressure was calculated with a rho G vector, which should be the case, then you would get the buoyancy force automatically. But because creeping flow has superposition, we just know that it will have a buoyancy force separately, and then we just use that as a drag force. Okay, so it's not double counting. It's just in this case, because when we are calculating the pressure force, we did not include gravity. So that's why we can basically get away. Okay, does it clarify? If we include gravity here, then you will not need to include buoyancy. It will automatically be included in your pressure forces. All right. Okay. So it was a long first part. So let's take a 5-minute. Let's come back at 1:05. Okay, 1:05. And then in the remainder 15 minutes, I'll introduce inviscid flows, and then we'll start more on Wednesday. Yes, that's it.
Could you please explain these argument again?
Sure. Yes. So what I'm saying is, I don't have the book with me, but basically when we use the pressure, right? When we calculate the pressure using this, then I don't have any gravity dependence on this pressure. So when I calculate the force, then I calculate the force which is only because of the velocity. But in reality, if something is like velocity, when the solid is dropping, then I should include gravity. And in that case, the pressure will have a dependence on gravity, which is not included right now in the drag calculation. So I calculate it separately.
Okay.
Make sense?
Because if you did all once, you have to change.
Absolutely correct. Hi.
So, right, when you talk about parallel plate.
Yes. Yeah.
So for these study things, problems that are solved, but if you're oscillatory,
Correct. Yes.
you make a scaling argument that your perturbation.
So depends.
Scaled by that, and then you do like small parameter expansion, like we've seen the relationship.
Correct. So that depends on which kind of theology. So there's small angle COS, which is small angle oscillator shear, in which case it has the perturbation expansion. In which case, so in that case, you just put perturb expansion, and then you write the solution as an infinite power I omega t or sin omega t or cos omega t solution. But then there is also this modern idea of large sample oscillator shear, which is more exact. So which is kind of not trying to do this perturbation harmonics. Yes, and it's much more complex. Correct, non-linear, absolutely. So when you do a small perturbation, it is actually just that. It says that there is a time, we don't ignore the time dependent term, we just make it an EI omega t, and then we still make it an ODE, but you just solve it like the problem is still not fully complex.
Just same thing.
Same thing, just yeah. So you have this extra time dependence to models. Make sense? Yeah, I'm not also very big kind of expert in biology, but that's my.
In Europe, they started.
On the exam, is it going to be similar to the homework where like you're going to guide us through like step by step, like do this and you should get something like this?
I would say, yeah, it would be similar. Structure of the solution, some of the beta values or some values, let's say, something that you have calculated. You say, okay, this is the portion of the matrix, but find K. It will not be like, you will not be master all of these steps without any guidance. But obviously you will not have to have students like that. Okay. Just giving the answer.
Yeah.
You mask the answer. Like that. Students who because some of the students just skip all the sudden, oh, we got the answer.
Yeah.
It's one of the that feedback. And that's okay.
That's it.
But that's how I careful because never know more than 6. Yeah. But it's careful because they're not meant to give one pill. But like obviously, but it's still like
I'm a big fan of like I'm a big fan of like
All right, everyone, let's get started. So it's 1:05. I want to make sure we start the part 2, which is inviscid flows.
Fair enough.
This is chapter 9 in Dean. This is chapter 9 in Dean, and what this really is about is the limit. Remember that Reynolds number is rho UL by mu. And this means that now we are thinking about rho e going to infinity. And that's sort of the scale we are thinking about. First, we were thinking about Reynolds number much smaller than 1, when we were always ignoring the other parts of the equation. Now we are going to the other limit, which is Reynolds number going to infinity. And that's really chapter 9. So we have moved past chapter 8. Now this is chapter 9 of Dean. And what is, why should we care about this sort of limit? So I showed you Reynolds number small is for microorganisms, and all of that. But this is really, high Reynolds number flows are really very important for engineering systems. So If you're thinking of automobile design, that's always at high Reynolds number. Windmill design, very important for energy. It's a very, very complex design process. And obviously we'll not get to them in the detail, but we will start talking about these things, how to think about these, designs and flows. But this is all a very, very active area of research. And to give you an example, I was talking to an expert in windmill design, and they were saying that they have not been so good with windmill design that they're able to get 97% of efficiency, the really high levels of efficiency. It's all engineering design. Okay. But more recently, like all of the COVID-19 research, which has now kind of been proven, with a lot of certainty that it is airborne. That's why we were all wearing masks, right? In airplanes and so on, there's a lot of circulation that happens. And so whether airplanes are safe or not, and all of that is really high Reynolds number flows. This happens at a really large Reynolds number. And so there are a lot of applications of high Reynolds number flows. The most you might have heard that turbulence remains the last unsolved problem of classical mechanics, which is basically high Reynolds number flows. Okay, so this is a very active area of research. We will discuss the basics. We will not go into too much depth of this topic, but I just figured that I will, kind of share this sort of background. Okay, so let's think about some numbers. So if you are kind of driving within Boulder, let's say, then I don't expect you will go much more than 20 miles per hour. Most roads will have that. So let's say you have an automobile. You're driving. So this is your car, and let's say your velocity is something on the order of 10 meter per second, which is 36 kilometer per hour. It's a bit about 25 miles per hour. Okay, so that's something like that. Now the length of the automobile is on the order of 4 meters. Okay, and then density of the air is 10 to the 5 Pascal seconds. Viscosity, viscosity is this, and density is 1 kg per meter cube. And the Reynolds number rho u L by mu comes out to be, if you do the calculation, it will come out to be something on the order of 4 times 10 to the power 6 with the SI units all plugged in, then you'll get something like this. So as you can see, something which a very, very, moderate driving speed, you can get such high Reynolds number. It's really, really high. And naturally, we have to think about this limit. It's very practical limit. So low Reynolds number is a very active area of research because there's micro scale. So we're going much, much finer length scales, but this is usual life, which will basically, meters and so on, you'll get very high Reynolds numbers, right? So from that perspective, now let's go to our governing equation, because that's what we want to understand. Our governing equations are rho del V by del T plus V dot del T, V dot del V minus grad P plus mu del square V plus rho G, and del dot V is 0. Okay. So these are the two governing equations we have to discuss. And again, if you can solve them, you don't have to worry about anything, but we can't solve them, right? That's why we have been kind of talking about unidirectional flows, near unidirectional flows, lubrication flows, because a general solution for this equation does not exist. So now, if we have this equation, and I'm saying that you basically want to ignore sort of the simplest idea is just drop this term off, right? Because viscosity is 0. For Reynolds number going towards infinity, viscosity is 0. We can kind of just drop this term off, right? So that's it. So we have essentially a new governing equation. Now note that we're not, for the first time, we are not dropping the left hand side off. You always somehow or the other, we never kind of took this into account. We always ignored it, but now we are ignoring the viscous term. Okay, so that's the big change. We are ignoring the viscous term. Any interesting things that happen when you ignore that term? Do you think there is anything kind of peculiar? What do you think about the number of boundary conditions? Do you think they will remain the same when I'm dropping a mu del square V? Or do you think it will change? thoughts? So the number of boundary conditions are given by the order of the equation, right? How many derivatives you are. If you have 5 derivatives, you will have 5 conditions. So now I had a second derivative with velocity. I have removed that, and now I'm only left with the first derivative of velocity. So remember, in inviscid flows, when you do that, you cannot satisfy no slip. This is a very, very big important point. You cannot satisfy no slip. Okay, so don't forget this. You cannot satisfy no slip. Remainder of the boundary conditions will remain the same, but no slip you cannot satisfy because you have dropped that term and we reduced the order of the equation. You cannot satisfy no slip. Okay. So that's point number 1. The second point is that let's assume steady system. Assume steady. Then I can say we have something like V dot del V plus grad P by rho minus rho G vector. The minus G vector is equal to 0. And del dot V is. So these are my governing equations now. V dot del V plus grad P by rho minus rho G vector, and that gives you the equation. So we have studied, so we can assume this. Another thing that we typically assume, and we will discuss this a little bit, but I prefer to not, I will basically suggest to not worry about it too much. It's a matter of a little bit of detail, is we'll assume it's irrotational flow. Irrotational flow, where essentially what it comes down to be is that you kind of say that curl of velocity is 0, and if you allow that, if you allow me to write that, you can transform this equation for steady, inviscid, and irrotational flow, and that this equation will become grad of V square by 2 plus P by rho plus GH is equal to 0, or V square by 2 plus P by rho plus GH is equal to constant. And I hope you can remember this. What is this equation called? Bernoulli's equation, right? This is the equation that you must have read in your courses. It's called Bernoulli's equation, but this is kinetic energy. This is your hydrostatic pressure contribution, and this is your potential energy. Okay, so you might have read it in terms of energy contributions, but this actually comes from, as you can see, from Navier-Stokes equation. Okay, which basically is how you can get this. And by the way, what is this V square? Velocity is a vector. So V square is Vx square plus Vy square plus Vz square. So it's the magnitude of the velocity. And what is this? H is the height above us, height above a reference plane. Height above a reference plane in the direction of gravity. So, any questions here? So do you see how we've gone from Navier-Stokes equation to so many different varieties, but now when we go to the other limit, we have essentially kind of gotten to this point. So you take the, yeah, so it's a, that's a, the book has a derivation. It goes through all the steps. I'm just not skipping some of the steps. Any other questions here? Does it make sense? So should I just, can I just solve this? Like, I have one equation. I have 4 variables, Vx, Vy, Vz, and pressure. That's sort of a problem, right? So what is something that I have kind of missed? So we derived this. So those there are 4 equations on top, right? V dot del V plus grad P by rho minus rho G. Now I have reduced it to a scalar equation. So should I just give up? Like, what's the solution? Right? So the thing is, what we have not exploited is the continuity equation. Okay. So don't forget that we have not exploited the continuity equation. And essentially what happens because for omega equal to del cross V is equal to 0, you can essentially write velocity as grad phi, where phi is the potential scalar. It's called the potential stream function or potential function. So I went ahead. It's called the potential function, and I'll talk about how this is also related to stream function in a second. But this is called the potential function, and it is essentially V is equal to grad of phi. Okay, so that's basically what you get. Just take a scalar phi, and because del dot V is equal to 0, Laplace of phi is equal to 0. Laplace of phi. So you can solve this equation basically. So this essentially, so solve for phi. Actually, let's just give a second. So this is one option. The alternative option, and that I'll skip over the details. Alternative option is to actually use del square psi is equal to 0 or E square psi is equal to 0, where psi is the stream function. So for inviscid flows, you can use either or. It's up to you. Okay, so in inviscid flows, the idea is you can go either. You can say velocity is my grad of phi. My governing equation is del square phi is equal to 0, or this is alternative 1. This is option 1. Or you can say del square psi is equal to 0 or E square psi is equal to 0, and velocity is given by table in the table. I think it's 6-4, but let's just check. Velocity from table. Just give the right number to make sure I don't. I'll come back 612. Okay, 612. And so here you will solve for psi, solve for phi, get velocity, solve for psi, get velocity. Okay, and then both of them, either options, essentially you will use, and you can calculate pressure using the this can be used to calculate pressure. Okay, so the velocity is calculated either through stream function or potential function, and then once you have the velocity, then you can use this to calculate pressure. So that's kind of the workflow. Okay, what's the difference? Don't forget, while solving this, no slip does not apply. Make sure no slip does not apply, and so your basically all other boundary conditions are same. All other boundary conditions are same. Okay. So in the next lecture, what we will apply this sort of framework, inviscid flow framework, to calculate drag on a cylinder. Homework, it is drag on a sphere, and it's much simpler than your Stokes law, because as you can see, it's only second order. It's del square phi. It's a Laplace equation. It's not something that is as difficult. It's actually just I would say it'll only take us 20 minutes at max to do that problem, or 30 minutes, and in the remainder of the time we'll do the review. And in your homework, like I think that this problem is much easier than your Stokes law. So So we basically will discuss how to calculate drag. Remember, in drag, you have two components, pressure and shear stress. Can I have shear stress in inviscid flows? No, viscosity is 0. So it simply becomes a pressure calculation. It's again much simpler, and we'll discuss that next time. But hopefully you can see how we have come together and build a subject. Yes, Colin.
So then you need two boundary conditions in phi.
Correct. One is at the surface and one is far away. Yes. And we'll talk about that next time. Yes. All right. So with that, thanks everyone. And then we'll continue on Wednesday. I have office hours now. If anybody has questions, I'll be happy to answer your questions.